Hey everyone, first video for Wednesday's SI, October 16th. I got to get into some reactions basics. Before we actually get into the reactions, some review from last chapter a little bit, stuff that was hidden in the textbook but not really assessed over, but that are important to know for these reactions. First thing here, we're going to talk about primary, secondary, and tertiary carbons, carbocations, alkyl halides, just some terminology we use and some of the reasoning behind that. Our reactions are going to be dependent, might change depending on whether we're in primary, secondary, or dealing with tertiary structures. So just going to fill out this table real quick, talk about carbocations. Will be a shorter video. I imagine the ones that are going to be shorter than usual as well. I always say that, and they always are longer than I want them to be. Okay, first of all, we have what's called a primary carbon. Okay, and I'm going to circle this carbon here on the end. Okay, this primary carbon, primary meaning one, it's only bonded to one other carbon. Notice how this carbon here is bonded only to one other carbon. Okay. This here as well is a primary carbon. Just what we can call it. Just that there's one carbon group on it, three hydrogens. It could be three of groups of any kind. So long as it's bonded to one carbon, that's a primary carbon. I can draw the same structure, and you can probably guess. The carbon in the middle here is a secondary carbon. It's bonded to two carbons. Carbon in the center. Tertiary carbon. Three carbons bonded to that central carbon. Okay? I could also have a quaternary carbon. It's like that. Think of it as four methyl groups bonded to a quaternary carbon. Okay? All right. Now we can also have carbocations, and it's very, very similar. Okay, carbocation here could be in this location, and the carbon that the carbocation is bonded to one carbon. This is a primary carbocation. Secondary carbocation, tertiary carbocation. Okay, we can't have quaternary carbocations, otherwise we wouldn't have a carbocation. We'd be bonding to four groups. We wouldn't have that positive charge. Okay, and we'll move on down to alkyl halides. Okay, so alkyl halides could look something like this, where this chlorine here that's bonded, the carbon that's bonded to is bonded to one carbon. Okay, so the carbon the chlorine is bonded to one carbon, one primary. Secondary alkyl halide, the carbon the chlorine is bonded to has two carbon groups or carbons coming off of it. Okay, they could be however long. You could have benzene over here, you could have whatever you want, so long as that carbon there is making two carbon bonds, secondary alkyl halide. And finally, you have your tertiary alkyl halide. Good. Awesome. Tertiary alkyl halide. All right. Sweet. Again, can't really have a quaternary alkyl halide. We have carbon making bonds. So we're going to use those when we get into reactions. We're going to talk about sterics, and we're going to talk about carbocation stability. Okay. So of the three carbocations I have drawn here, okay, one is preferred over the other two. in between the lines in the last chapter, wasn't discussed much, wasn't tested over, but alkyl groups, okay, carbon chains are very slightly electron donating, okay? They're gonna donate electron density towards something like a positive charge, okay? Knowing that, okay, tertiary carbocations are the most stable, okay? Most stable are our tertiary carbocations. I have more alkyl groups than the other two that are donating electron density towards that positive charge and making it more delocalized. It's the same concepts as before. We want to make that charge delocalized so we're more stable. Get yourself a tertiary carbocation and you'll do that, okay? And then we would just go down. Now we have two groups, okay? Secondary carbocation, and the most unstable, the most reactive, I suppose, would be something here like a primary carbocation, okay? Most stable, least stable. Now I have a structure that looks like this with a carbocation in a, you guessed it, primary position, okay? Now, there's a way to make that this molecule can be more stable and likely would undergo this, okay? Something called a hydride shift. Not very common, but I do want to bring it up just in case. Now, we would have a hydrogen here in our stable tertiary position. Hydride shift, okay? That hydrogen is going to shift onto this carbon here, more specifically the bond, onto that carbocation position there, okay? Notice that's gonna leave, okay? We lost a hydrogen bond here, so now we're only making 3 bonds. We gained a hydrogen here in the primary position, where before we were making 3, so now we're gaining 1, we're making 4. Hydride shift. I have now gone from a primary, remember, a very unstable carbocation, to a more stable tertiary carbocation. Okay. Last thing I'm going to say about primary, secondary, tertiary, quaternary. Notice the sterics, the steric hindrance. It's something in a tertiary, especially here with alkyl halides, because these are going to be a lot of reactions that we have. Halides are good leaving groups. We're going to be dealing with these a lot, okay? Notice that something in a tertiary position, how much steric hindrance we experience compared to something in like primary, okay? You can even draw hydrogens in over here, okay? A lot more difficult to get to that carbon there, and it is our carbon here, okay? Just visually we can see that, but know that coming up because it's going to depend on whether we do nucleophilic substitution 1 or 2 reactions based on steric hindrance. So, all right, that's the first video.